Okay, in this video what we're going to learn is how to incorporate Zernike coefficients into a Zernike surface by direct input using the DOE and CGH calculator. So I'll assume that you know how to open up the calculator, and this is just the default window. Of course you can change the sampling and the master size and these parameters as you'd like. But I'm not going to concentrate on that right now. We're just going to use the default values, and we're going to show you how to make that Zernike surface. So first of all, I'm going to save the project as something like DOE project Zernike A or something. Okay. And go into add, edit DOE elements, and this is the default. We're not going to use these guys right now, so let's just cut those guys. And from the drop down menu we're going to do a Zernike surface. So we'll paste new on that, and again remember that you have to kind of hit off and then back on the element, and it'll come up to this kind of a panel for you on the element parameters. And the size is like it is before, just the size of that element. Offset of the center, usually I leave that at 0. What quantization you want to use, the radius over which the Zernikes are calculated, and then the coefficient vector, and then something called the fringe scaling factor. Now, to understand what these guys are, what we can do is go to the DOE calculator help file, and that's right on the website. If you go to the Optiscan website and go under documentation, then you can select the DOE and CGH calculator, and it'll come up like this. And what we want is the Zernike surface description on page 9. So we'll go down to page 9, and what you'll see is that the coefficient vector, the radius is the radius over which the current Zernikes are defined, units in meters. Coefficients, forgive the more English there, coefficients are input. Okay, well, I'll show you about that in a minute. And basically it's just saying that you can go into the box there and change the coefficients as you like. You can also, when you hit the calculate button, you can load a file. In this video what we're going to do is just direct input, and we'll understand what those coefficients are in a minute. Now the fringe scaling factor is something we're just going to leave at the default of 1 for now. And what that is the if you use a for example, if you're testing coefficients with large order of fringes, then you might want to not use each see each fringe, because you wouldn't be able to see the pattern. So you can set the fringe scaling factor to see like every 10th fringe or something. Alright, so to understand what the coefficients are, we'll go to another help file, okay, another help page. Look under HTML-based help pages, and then it comes up with a screen like this. We can hit on table of contents and go down to the lens object under the aberrations panel to see about the Zernikes. This is actually a description that is primarily about the lens object that we'll learn about in a different video. But if you scroll down, you'll see the Zernikes, and that's consistent throughout Optiscan about how we do that. And it has a table there that describes how we load up the Zernike coefficients, what the polynomials are, and this is, I use the expansion from Malakara, and their description, and that is you can load up to any number of coefficients. That's not a limitation here with the table. It's just for space. I didn't put in that many. You can look in Malakara to see the algorithm for generating a larger number of terms. The ZVec vector has elements that are described as the first two elements are the order of the expansion, then the number of points for the initial calculation, and then actually starts the Zernike coefficients. Starting at Zernike coefficient 3 is just the constant term, and then up in this chart up to fourth order through 17. The example here is actually just a third order calculation, so there's only 12 coefficients in the elements in the vector, and that's element number 11 there, which would be third order coma along the y-axis as the default. So let's look at the Optiscan default coefficient vector, and that's what's right here. So 3 is third order, 100 points for the initial calculation, and then that's 1, 2, 3, 4, 5, 6, 7, 8, 9, or actually that should be 11, 12. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So it's a coefficient of 1 there. So if we look back on our table on number 11, that's that third order coma, and that includes the tilt to minimize RMS. So let's just look and see what that gives us with the when we hit calculate. So when we hit calculate, then it'll ask if we'll load a new Zernike coefficient file. We'll do that in another video, but say no now. And you can save it as a bitmap file if you want, if you're going to write out a phase plate or something, but right now let's just not worry about that part. And you can see the math there, and this would be 3 waves of coma compensated with tilt. So these are just the profiles, and this is what it looks like for minimizing the tilt, minimizing the RMS wavefront aberration as defined by the Zernikes. Let's go back in and take out that tilt by adding in a second term up here, ZVAC 5, which is tilt in that direction. And what we'll do is we'll just put in a factor of +2 for coefficient 5 there to change that value and take out the tilt. And then we should have 3 waves of coma. So when we go back to the coefficient vector here, let's find coefficient number 5. There's 3, 4, 5. We'll put in a +2 to cancel out the tilt of the coefficient on element 11, and hit calculate, no, and there we go. Okay, that's 3 waves of coma. We can see that in the profile of the exposure. There's 1 wave, 2 waves, 3 waves of coma. So that's it.